and elegant. It gives a geometric flavor to what we know as probabilistic inference. It shows that this probabilistic inference is some form of logical deduction, and it avoids problems with conditioning on sets with probability 0. What I'm going to move next is I'm going to show that it allows us to derive the other models, such as lower expectations, sets of conditional expectations, and so forth, but that it is more general and more expressive than these models. So that's what I'm going to turn to next. So here we are. We're going to go towards other models. So we start out from sets of desirable gambles. We're first going to go to lower expectations, then to mass functions and sets of them. And that's it basically. And then do the conditional versions as well. So let's start with lower expectations. We start from a coherent set of desirable gambles. So that's our starting point. This is what you see here. We have this coherent set of desirable gambles. And then the idea is I'm going to associate with this coherent set of desirable gambles two functionals, a lower expectation functional and an upper expectation functional. The lower expectation functional will be defined as a supremum binding price. So the idea is that the lower expectation of a function of a gamble will be the supremum price mu that I'm willing to pay in order to buy, or that you are willing to pay in order to buy the gamble G. So G minus mu is the transaction or the reward function for buying the gamble G in return for a fixed amount of utility mu. That is desirable to you, so you're willing to do that. And we're looking at the supremum mu for which this happens. This is your lower expectation. The upper expectation is defined as the smallest mu, the infimum mu, such you are willing to give away G and get mu in return. So selling G for a price. So it's an infimum selling price. The infimum selling price that so such that you find this selling transaction desirable. And that is your upper expectation, or I define that as your upper expectation. Again, there's a conjugacy relationship between the two. The upper expectation of a gamble is minus the lower expectation of minus the gamble. Yeah?
I think there's another definition in the ballpark here, which is sort of top of the buying price such that you wouldn't disprefer it, you wouldn't find it undesirable.
You could do that as well.
Is it just formally equivalent?
It's not necessarily formally equivalent. It will be in certain cases. You could do this, but this is the easiest way to deal with it. That being said, let me come back to that at the end of the. So remind me at the end. I will say a few things about that. Okay, so let's look at what these transactions look like. So I have this set of desirable gambles here in 2 dimensions. Let's say heads and tails. I have the gamble G, and then G minus mu is just, so I draw this line that is parallel to this line here, and the constant line. I'm drawing that line, and then so these are values mu, they increase, and at some point, for some mu, I will stop being in the set of desirable gambles. Yeah? So here at the border is exactly where the mu, the G minus EG resides. So for this value mu equal to E lower G, I reach the boundary of the set of desirable gambles. And if you look at it geometrically, that is what happens. Yeah? So this is quite interesting. So the idea is that if G increases, if mu increases, then I tend to eventually get out of the set of desirable gambles. So at some point there will be this set will for some mu, my G minus mu will no longer be in D, and then the largest one for which it is still in D is the lowest. It's actually also the lowest one for which it is not, because it's border, right? It's border condition. So in that sense, if that is what you meant, then I would say that. But it's not what you meant. Depends on what you call undesirable, I think. Yeah. Fine, and then the upper expectation is completely the dual thing. And it's easy to see. I'm not sure that I have to actually do the calculations to see that the upper expectation of G is minus the lower expectation of minus G. Do you want me to do the actual proof of that? It's fairly easy. Similar to what I've done before. So let me look at the upper expectation of minus G. It is the infimum of all the mu in R such that mu minus G is in D. This is just G plus mu in D, which is G minus mu in D. So if I replace minus mu by minus mu, this becomes infimum of minus mu prime in R such that G plus, G minus mu prime is in D, which is minus the supremum, because minus turns the minimum into the maximum, minus the supremum of the mu prime in R, such that G minus mu prime is in D, and this is minus the lower expectation of G. So the upper expectation minus G is minus the lower expectation. That's the conjugacy relationship between the two. Okay. So if I start out with a set of desirable gambles D, I can define this lower expectation functional. And it turns out that the properties of this lower expectation functional, or that this expectation functional satisfies these three properties, which are the basic properties. The lower expectation dominates the minimum. It is what we call super additive. The expectation of the sum is greater than the sum of the lower expectations. And it is positively homogeneous or non-negatively homogeneous. If I have a non-negative constant, I can take it out of the expectation operator. What happens with negative constants? If I have a negative constant, what happens?
You change it's like upper bound and minus.
Yeah, you can use a conjugacy relationship. So then what you do is you say that this negative lambda is minus the absolute value. You take the minus out, turns into an upper expectation, and then you can take the lambda out, and then you can combine the lambda again. So everything that happens, the lambda, the absolute value, and the minus again into lambda. So you can take the lambda out, but the lower expectation turns into another. That is what happens if your constant is negative. So you have something like this. Okay. There are a number of derived properties. These are good exercises. They're really cool. So together with the lower expectation is always dominated by the upper expectation. And both of them are squeezed between the minimum and maximum function. 5 is very cool. What we call the combined super additivity properties. So the sum of the lower expectations is smaller than the lower expectation of the sum. It's smaller than changing one here to an upper. Gives me an upper bound for the lower expectation as well. And this is bounded above by the upper expectation, which in turn is smaller than the upper expectation. So it's all kinds of interesting things happening there. Right, there is this constant additivity. If mu is a constant, then the expectation, the lower expectation of g plus mu, I can take that out. Constant, I can take a constant out, an additive constant out of the expectation operators, or the lower expectations of operators. And these are normalization conditions. The expectation or lower and the upper expectation of a constant are equal to that.
The second property is like the sum squared and the sum of the expectations. Why is not equal?
The second one?
Yeah, the second.
Superadditivity, why it's not equal? Well, that's a good question. In fact, what I'd like you to prove is prove that 2 holds as an exercise. So I'm returning the table. And then try to see why it's not an equality. So I tried to prove from this. So the idea is you have this expression. So you have the lower expectation of a function. It's defined in this way. D is a coherent set. So you can use the coherence of D. So the 4 coherence properties of D, it's a convex cone that contains all the positive counts and doesn't contain 0. That's what we can do is show, using this formula, that the lower expectation satisfies the superadditivity property. Sorry. Okay, let me give you, so take any alpha that is smaller than the lower expectation of G, and any beta that is smaller than the lower expectation of H. Yeah? Since this is the supremum of all the alpha for which G minus alpha is desirable, this means that since it's a supremum and alpha is smaller than the supremum, this means that G minus alpha is desirable by definition of the supremum. This means that H minus beta is desirable. As a result, because if I have two desirable things, then their sum is also desirable. This means that H plus G minus alpha plus beta is desirable. And if I now use the definition of a lower expectation as a supremum, all the values for which this is desirable, this tells me that alpha plus beta must be smaller than the lower expectation of H of G. By the definition of the lower expectation, because the lower expectation is the highest one. So what I have is that for any alpha that is strictly smaller than this and any beta that is strictly smaller than this, their sum is strictly smaller than this. So take the limit of alpha going to e.g. H and the limit of beta going to here. In this expression, this limit is preserved. It preserves the inequality. That's what limits do. And so I find that the limit of the alpha, which is the expectation of G, plus the limit of the beta, which is the expectation of H, must still be smaller than even in the limit. That's the simplest to find. The maybe simple ones, that's the simplest to find. So why don't we have equality? So why don't we have, or what happens if we do have equality? Suppose that we have equality for all gambles. Take H equal to minus G, which should work in particular. That tells us that the expectation, the lower expectation of 0 is equal to the lower expectation of G plus the lower expectation of minus G, and this for all G. The lower expectation of minus G is the upper minus the upper expectation of G. So this is 0. This tells me that the lower expectation is equal to the upper expectation for all G. So then that means that the model. So as soon as we have additivity rather than superadditivity, the model is. And we don't have that the model is precise because we're only working with a cone here, right? So in the if the cone were a semi-space, then it would be, we would have additivity. Coming back to that later. At this point, we're only working with a cone, and it's the fact that it's only a cone, make sure that there will be cases where the equality will not be set. Okay?
It's the case of coherence.
The coherence of the G, is that what you mean?
It's
Yeah.
against.
It's again coherence, is that what you said? against coherence, no?
I thought you said if we assume equality, then we would violate one of the criteria.
No, you don't violate the coherence. You just force your lower equation, your lower to equal, and that only happens when you have a sentence trace. So this is the condition. So additivity, in a sense, is just equivalent to precision.
Is there any geometric equation for subtronic? Is there any geometric equation? Because I mean, you have a like G minus lower expectation of G. Is there like a geometric interpretation of intuition behind these inequalities?
These inequalities, the additivity inequalities, probably. Probably I haven't thought about it, but there might be. Yeah. It's a good question. If I give this lecture ever again, I'll try to think of the geometrical equation of why it must be. Yeah.
Just I was thinking about the geometrical. I think it's very precise and you have a straight line, and it's easy enough to show that they are connected. It's like a distance, but they're parallel lines intersecting this one line, so they add up to sum the vectors. And then when you shift the line into a cone, the sum of these vectors increases slower than the vectors you're adding up because of the yeah, there's similar triangles with like bigger sides. So yeah, there is like
there's an argument.
mathematical.
Actually, I think exactly this type of argument is something that I'm going to give you as an exercise, as a homework later. So I decided to give you a homework for those who really don't want to party tonight. There will be a homework, and it's exactly one of these questions to explore this idea. But let's wait for that later. Okay. Right. Another interesting thing, perhaps, is that these three properties define, the three properties say what it means for a functional to be a lower expectation. Yeah? Now, turns out that you can extend this definition of a lower expectation from, in this case, the set of all gambles, which is in this case just a finite dimensional linear space. But we can extend this same idea when you replace this the space of all the gambles, the linear space of all the gambles, by any real number space. The space that doesn't even need to have constant, so you can just extend the same idea, and the arguments remain the same. I will argue later that in this case, it's not really justified to call this thing an expectation, because there is no longer any probability that you can, or no longer necessarily any probability related to that. And so Definiti already had this idea for precise probabilities. We extended the notion of the expectation operator to, I think, Fréchet spaces in general, but he calls, and he already noted that in such spaces there are not necessarily events. So events disappear, you only have functions, and events are not necessarily in that space. And so you can no longer define probabilities. And so it's not really useful to talk about the expectation associated with the probability, and this is one of the reasons why he introduced the notion of prevision rather than an expectation. Because these things are no longer necessarily expectations associated with probabilities. And this is particularly what happens, I think, in quantum mechanics, where sometimes you get functions that are expectation functionals that are, well, there are provisions that satisfy the provision properties, but it's almost impossible in the normal sense to associate them with probabilities of events. So these probabilities may not exist, they may not be there. This is one of the reasons why, in that case, we would prefer to use the notion of provision. Right. So let's look at this picture again.
You define the expectation, it doesn't depend on probability.
In this case, no, but in the word expectation, typically what we expect from an expectation is something that is associated with probability. So what I could have done, or should have probably done, is call this a lower provision rather than a lower expectation. But then, yeah, then your intuition will completely fail. And in this case, because we will see that it can be associated with probabilities, it's probably okay. Because the underlying space is a space of gambles, and you can define events on that space. That is not necessarily always the case.
How do you define sequences here? So it's a sequence, because you have a finite space, so you need probably sequence of elements. Okay. Okay.
Okay, so let's look at this picture again, right? So we know that when the mu is equal to the lower expectation, we are on the border. Almost by the definition of the lower expectation as that value for which we are on the border. So this means that this distance, if I project downwards, the distance between these 2 points in the x direction, but also in the y, in the heads direction and in the tails direction, this distance is just equal to the lower expectation. This means that for a gamble that is already on the border, the lower expectation must be 0, because that's the distance. So this tells me that the gambles on the border are completely characterized by the fact that their lower expectation is 0. That defines the gambles on the border. The border is defined by the property lower expectation of the gamble is 0, because that distance between the border and the gamble is then 0. If this distance is positive, then I'm inside the blue region. If the distance is negative, I'm outside the green region. So I have these three possibilities. The lower expectation is positive, which means that the gamble lies in the interior, topological interior of that set of desirable gambles. If the lower expectation is negative, strictly negative, means that my gamble lies outside the closure. Right? It lies outside, or even outside the closure. It's not even on the border. And if it's 0, it's on the border, it's on the boundary. So these gambles, the gambles that are in the interior, for which the lower expectation is strictly positive, following Pisarelli, I will call these strictly desirable gambles. If I have a set of desirable gambles, these are strictly desirable. They are in the interior of my set of desirable gambles. And if the lower expectation is 0, I will call them marginal or marginally desirable. These are on the margin, in the boundary, border of the set of gambles. So all the gambles on the border are characterized by the fact that their lower expectation is 0. But remember from what I said in the previous lecture, that whether the border is included or not depends. Sometimes the border can be in there, sometimes it can't. This means that by looking at the lower expectation only, I can't know whether the gamble is inside or not. Because it may be inside or it may be outside, depending on whether the border is included or not. So we can't know if the gamble is inside unless it is always excluded. Yeah? Unless the border is always excluded. If the border is always excluded, if my set of desirable gambles is open, in that case, I know that that this will only happen if I'm outside. Otherwise, because the boundary may be excluded or not, depending, I can't tell from the lower expectation whether the gamble is inside or not. What does this tell me? That in this very simple sense, desirability is more general as a model than lower expectation. Because, and this is something I said before, lower expectations are typically always Archimedean models that can use real numbers to determine whether something is desirable or not. I can't do that in a very simple sense. I can't do that for desirability because some orders may be included and some may be excluded. I said nothing about that. So desirability is in that sense more general. In that very simple sense, more general, more informative, if you want. And I think that Teddy will have much more to say about that kind of distinction and Archimedeanity later on. Okay, so this, yeah.
Sorry, on the previous slide, your diagram. That's just a bit confused.
Yep.
Because it looks like the length of the blue vector is the lower expectation, but then.
No, the length of the blue vector is not the lower expectation, right? Because what I'm doing is I'm subtracting. So the idea is the following, right? If I have a mu here, a point here corresponds to a constant u here. Yeah? So this length is the square of twice mu. The square of So it's not the length of this vector, but it's the length of its projection onto any of the axes that is equal to mu.
Basic question. Can you remind us of the definition of Archimedean?
Well, definition of Archimedean, that is the problem. So in a very wide sense, Archimedean means that I can use, in a way, I can use a single real number if you want to represent whether something is in there or not.
So we have Archimedean like in the real time system.
The fact that you can use real numbers, that real numbers are enough. That is, if real numbers are enough, then you use it. Teddy, more or less, agree?
Always more.
Always more. I know it's more subtle than that, and that there's much more, but in this case, just if you can use a real number to determine something, in this case, the real number is the lower expectation. If you can use the lower expectation to determine whether it's inside or not, this means that your model is Archimedean. If you can't use the lower expectation, then it's not Archimedean because the real numbers are not enough to distinguish between the wrong and not.
So that means there is nothing outside the real number or the lower expectation that can change whether it's inside or out.
I didn't get that, sorry.
So that if it's Archimedean, there is nothing outside, like besides the real number of the lower expectation can change whether it's inside or out.
But if you could have something more than the real numbers, and then, for instance, 2 real numbers, 3 real numbers, and then so then you will have lexicographic ordering. So if you have 2 or 3 or 4 real numbers, that would not be Archimedean in the straight sense. Right. Okay. Right. So this leads to desirability models that could be described as Archimedean. First one is strict desirability. So a gamble is strictly desirable if its lower expectation is greater than 0. But again, I have to add this, make sure that also the positive gambles are in there, because that is not guaranteed by the first condition. I have to add the fact that in order to make it a type of desirability, I have to add the background ordering in there as well. So that is the first one. Yeah. That gives, in our simple two-dimensional case, that means that the border is never included in my desirability. And then I have something that is called almost desirability. Almost desirability means that the lower expectation is greater than or equal to 0, and in that case, the border is included and 0 is also in there. Right, so that is it's not real desirability in the sense that 0 is also in there. It's a weaker form of desirability. It's therefore called almost desirable. Yeah.
Here, you find the large data starting from a coherent set, you still need this condition P larger than 0.
Yeah, I think so. Try to find an example. It's typically what, yeah.
Almost desirable,
Does not satisfy the desirability axiom. So it's not yeah, it's a weak form of desirability. You can define desirability by allowing weak dominance rather than strict dominance, and then have another form of desirability. But it seems that strict desirability is better when you use condition. Anyway, that is far beyond what I want to talk about at this point. I'm just mentioning that there are these two types of things that we could call Archimedean, because whether they belong or not to a set is completely determined by the lower expectation. It's therefore by a real number.
Question in the chat about, are we still assuming finite dimension?
Yeah. Many of these things still hold in infinite dimensions as well. I mean, but just not to complicate stuff. Right, so now I have talked about what lower expectations are. Let's now go to expectations, not just lower down. There's another question.
Sorry, maybe you said it. Why do we include the dominates 0?
Why put it there? Because this one does not imply that the name comes in there. So sorry, this one is not enough for this. So in order to, it's possible that you have a gamble that satisfies the second. And that is not very probable. Sorry. Weird. I'm confused. Yeah, it's the other. I'm confused. Yeah. So you have to make sure that you have all that these gammas are inside your that they're also there. Yeah? So this does not imply this. Yeah? And therefore you have to ignore them. If I were only to use this, then there might be gambles like this that are not in there. And therefore, if I want to set a desirable gambles, I need to include them. It's a bit like in the conditioning case.
So there are values that strictly dominate 0 in low expectations. The larger than, I mean, if I the only way they are larger than 0 means they can, but in every slot.
I'm a bit confused at this point.
At least one slot.
Let's think about it, and let's
Just take the vacuous. The lower, I mean, for something that's 0 somewhere, positive elsewhere, the lower provision would be 0, so not greater than 0. Those. Like, take for example, 1 0 0.
yeah. Okay. Okay. So let's now go to the precise case. Right. This is where I wanted to get to. So what we see is if I have a lower expectation, yeah. If I have a lower expectation, then I have the region where the lower expectation is strictly positive, that is that green region, order not included. And then, so these are the gambles that are strictly better than zero to you, strictly better than zero in that sense. The ones, the negation, if I put a minus in front, I get to the blue region, and that is exactly what I commonly see the gambles for which the upper expectation is strictly negative. So those are the ones that are strictly worse than zero. And then the remaining ones in the white region here is what previously I called the undecided gambles or the indecision. That's the region of indecision. This is not strictly true. There might also be in there gambles that to you are equivalent to zero. Right? You don't want to distinguish them from zero. They are uncertain, but to you they are exactly equivalent to zero. Now, if I have one gamble that is equivalent to zero, that I don't want to distinguish from zero, and I have another gamble that I don't want to distinguish from zero, what can I say about their sum? I typically also will not want to distinguish it from zero. Right? The sum of two zeros is again zero. So that means that this region, that the gambles that I assume to be equivalent to zero, will constitute a linear space. Because if I have a gamble that is equivalent to zero and I multiply it with any number, also be equivalent to zero. Won't change. So all the gambles that to me are equivalent to zero constitute a linear space, because I can take sums and I can multiply them with real numbers and it will still be equivalent to zero. So the equivalent gambles will be inside this white region, and it will be a linear space inside this white region. You see two possible ways of doing that in this case. That is, if only zero is equivalent to zero, and I have just a null space there. Or in this case, it could also be a real line in there. Gambles that I consider to be equivalent to zero. And then all the other ones are the ones that are, they're not equivalent, they're not strictly worse, and they're not strictly better than zero. So they are undecided, there is a region of indecision there. So the question is now, when is there no indecision? So when do I only have strictly better, strictly worse, and equivalent? Graphically speaking, it's when this wedge, these two wedges, will be a linear space, right? Because then those ones will have to be a linear space, because they're all equivalent to zero. So when is this wedge a linear space? That is the question. Yeah, and here is the homework. Homework is prove that if I look at the set of all the gambles in the wedge, in the two wedges, so all the gambles for which the lower expectation is smaller than zero and the upper expectation is greater than zero. Those are the gambles that are not strictly better than zero and not strictly worse than zero. Those are the remaining gambles. So when this is a linear space, show that this can only happen if the lower expectation is equal to the upper. Using the properties of lower and upper expectation. That is your homework. And I can only, well, I'm going to give you a hint, that is, use the figure, use your geometrical insight to prove that. So in other words, assume that, that these two wedges constitute a linear space, and then solve it. do something with that linear space. Okay. So for the time being, I'm going to assume that that is something that you've all proved. Yeah.
What is linear space?
Ah, linear space. A linear space. Sorry, I assumed that you didn't know that. A linear space is something that is closed under addition and scalar multiplication.
Same as convex.
No, convex is closed under convex combinations. So linear space is closed under linear combinations. Yeah. So it's a linear subspace. So the set of all gambles is closed under addition and multiplication. A real line, a line in there is also closed under addition. A line through the origin really is also closed under addition. So it's like a subspace. So it's closed under addition. Positive and linear combinations, not just positive ones, but all linear combinations.
Yeah, it says that the union of the two vectors is the linear space.
Yeah, that's this one here. So you can also already see that this set is invariant under taking a minus. Yeah. All right. Okay. Yeah. Okay.
What do you consider to be real value?
What is real value? Which number? Yeah, that's that's an assumption that's always there.
I thought you were looking at solutions.
No, this is looking at basic real value stuff. Okay. Yeah.
Describe something.
Yeah. Right. So this means once we prove this, we know that there is only no indecision when the expectation, lower expectation is equal to the upper expectation, because no indecision means that this region is a linear space. No? This means that this is a linear space because then there's only strictly better, strictly worse, and equivalent. So this is a linear space, then this is this means that this is just equivalence. And then there was no room left for indecision because that wedge is all equivalence. And there's no indecision left. So no indecision means that the lower expectation is equal to the upper expectation. And in that case, we call this common value of the lower and the upper expectation the expectation. Yeah? So that means that my supreme buying price for a gamble, that your supreme buying price for a gamble is equal to your infimum selling price for a gamble. So you have a price such that for any lower value, you're going to be willing to buy the price, and for any higher value, you're going to be willing to sell the gamble. So there's no indecision. We call that your fair price, because it's both a buying price and a selling price. So you have a fair price, or a provision in the language of the phonetic. What are the properties? Well, it's both a lower and an upper expectation, so it should be bounded by the minimum and the maximum. It should be both super additive and sub-additive, because the upper expectation is sub-additive and the lower expectation is super additive. So sub and super together means that we get equality. It should be greater and it should be smaller. Yeah? So we get equality. And we get the homogeneity condition for all real numbers. So this is the definition of an expectation operator on this linear space. And the gambles here in this linear space, in this case, are just the gambles for which the expectation is 0. I will denote by this bold P the set of all the expectations. Set of all the predictions. So that's a set of all the possible expectations. It's a notation I'm going to use. It's getting worse and worse. Right. So I've defined expectations, and now going back to probability. How do I go back to probability? Well, I'm in a space, so the set of all my outcomes are this curly X here. Remember, there were n values, a finite number of values. I've drawn the case here where there's only 2, but the argument is much more general. If there's a finite number of values, I can see that any gamble, any G, is a linear combination of indicators multiplied by the corresponding values. This is just writing down the value of the gamble in this n-dimensional space using the standard basis. So this Ix is just a unit vector in the x direction. Here, 1, 0 is the unit vector in the heads direction. And it is one of the standard elements of the standard basis of this linear space. It's just the simple unit vector here. This is the indicator of heads. This is the indicator of tails. So more generally, I can write any point, any vector in terms of the basis, in terms of the standard basis. This is just a way of writing that vector in terms of the basis, yeah? And the coefficients of that linear combination are, of course, just the values. This is almost trivial. If I plug in a value y here, g of y is just the sum of all the things here, the indicator of x in y, and the indicator of x in y is only equal to 1 if x is equal to y and 0 elsewhere. So I find that g of x is equal to g of x. Trivial. So this is, now I find that I can write this g as a linear combination of indicator gambles, and I have an expectation operator that preserves linear combinations. Yeah, so it turns a linear combination into a linear combination. It is a linear function. So I have the expectation of this linear combination will be a linear combination of the expectations. So the expectation of G will be the sum over all x of G times x times the expectation of the indicator. If I define the expectation of the indicator as the probability of x, or the probability mass of x, then what I see is that this expectation is actually the expectation associated of G associated with a mass function P. So what I always have is that any expectation operator that satisfies E2 and E3 takes this form. What does this P look like? Well, this P is just an orthogonal vector to this plane, right? So this is the plane where of the gambles where it is 0. Draw a normal to this and project it onto the probability simplex here. So this line, the line of all the mass functions, right? So these are the probabilities. So the coefficients here are P1 minus P, yeah? Where P ranges between 0 and 1. This is this probability simplex. Draw the normal line here, from here to here. Where it hits, that is the probability P1 minus P. In this case, yeah. So this is the mass function. This is this P that we have here. So P of heads will be P here, and P of tails will be 1 minus P. This is a geometrical interpretation. This is clear, this geometrical interpretation where I draw the probability simplex here. So these are all the probabilities that have its normal, the orthogonal to this, and where it cuts the simplex, this gives me the coordinates of the probability mass function. That what? E2 and E3? Yeah. E2 is additivity, and E3 is linear combination. So it tells me that this E is a preserves linear combinations. Yeah. So a sum is turned into a sum and I can take constants out. Okay, so this means that whether I use an expectation operator or a mass function doesn't really matter. Expectation operator corresponds to a mass function, and a mass function corresponds to an expectation operator. Of course, this is very trivial. I just needed to remind you of this simple mathematical fact. Okay. Again, here, I want to stress that we can still do all of this, define expectations, when the space of the gambles is not just the functions here defined on some set X, but any real Banach space. We still do everything. And then it may be necessary again to replace the notion of expectation by the notion of prevision, because there may not necessarily be any natural way to define events in that case. Okay. So if I have a quiz, so let me follow again or summarize again. Start from the set of desirable gambles D, and define lower expectation operators, upper expectation operators. When these go inside, I have an expectation operator, and that is equivalent to a mass function. So that's precise probability. The question is now, let me go back. So I know that when it's precise, it's equivalent to a mass function, to precise probability model. What if it's not precise? What if it doesn't coincide? When the lower expectation is not equal to the upper expectation, what happens then? So let's go back. We have a set of desirable gambles. We have a corresponding expectation operator. This should be lower expectation here. There's a typo here. This should be lower expectation. So I have this cone of strictly desirable gambles for which the lower expectation is strictly positive. I'm looking and asking you to look at the following set, the set of all expectations. So remember, P is the set of all possible expectation operators, all of them. And I'm looking at a subset of those expectations that dominate the lower expectation. So for any gamble, the expectation dominates the lower expectation in this gamble. I'm looking at all the dominating expectations. And I will denote this set by P of low, E lower. So it's the set of all the expectation operators that dominate the lower expectation. Oh. Yeah, I'll do just as well use the cursor here. So again, I've drawn the simplex here, the probability simplex. All the mass functions are points on this line. I'm taking in this case, what I'm doing is I'm looking at an expectation operator which corresponds to a semi-space, so a green area here, this area. Everything to the right of this line is all the gambles that for which the expectation for this expectation operator here, for which the expectation is positive. So this line corresponds to an expectation operator in this set, because everywhere it dominates the lower expectation here. So what I'm going to do is I'm going to look at this point, and I'm going to now look at another expectation operator that has this property. Again, this semiplane includes the cone, which means that this is satisfied. This condition is satisfied. So I'm having another expectation operator here, and again, I'm using the projection here. This is the probability mass function, and so on. And I do this for all the possible semi-spaces that include the cone, or in other words, for all the possible expectation operators that dominate the lower expectation operator. This is what's happening. So this is the mathematical way of describing what I'm doing here. I'm looking at all the semi-spaces that include the cone, and their semi-spaces. The border is determined by an expectation operator, and they correspond to probabilities in that simplex. Okay. This means that, because that, and then I have a theorem, this set of probabilities or expectation operators here is closed. Why? Because the inequalities here are weak inequalities. It's convex. If I take a linear combination here, it will still do this. It will still satisfy it, so it's closed and convex. And you can show that the value of the lower expectation is the minimum. So what I'm going to do is I'm going to evaluate the gamble G, or sorry, I'm going to take any expectation in this set of dominating expectations, take the expectation of G for that expectation, and then I get a set of real numbers. I take the minimum of that set, and that minimum is actually equal to my expectation. So what have I done? I've shown that this lower expectation operator that I started out with can be equivalently represented by a closed convex set of precise expectation operators. So these are mathematically equivalent. If I have a lower expectation operator, it is mathematically equivalent to specifying a closed and convex set of expectation operators, precise ones. So an imprecise model, in the sense of a lower expectation operator, is equivalent to a closed and convex set of precise models. And here I give you a graphical representation of that interval. This is the probability interval. In the case of two outcomes, this is a probability interval for heads. This is clear? Good, because we will be doing a little exercise now. Yeah. Should be what?
The definition of expectation.
An expectation is anything that satisfies these three properties. So it's a functional that takes gambles to real numbers that satisfies these three properties. So it is linear, it's a linear functional, and it's bounded. That's an expectation. I've shown that it is equivalent to a mass function here. And then the next step is showing that if I have a lower expectation, then this is equivalent to a convex closed set of expectations, of precise ones. Yeah. So lower expectation is always equivalent to a set of precise expectations. One-to-one correspondence.
So they all correspond to the size model.
What, sorry? Yeah?
Sorry, so they all correspond to the size model. Expectation, mass function.
These are the same thing. Yeah, that is those are the precise ones. Yeah. Yeah, that is what, right, because they are probabilities. So they are single probability measures, they are probability measures and corresponding expectations, so that's why I call them precise. And because it's just one of them. Whereas if I have a set of them, I don't have an imprecise model. And so the idea is, if I have a set of these precise models, I can go to an imprecise model by looking at the bounds. But conversely, if I have an imprecise model, I can always see that as a set of precise models. So there's this one-to-one correspondence between the two ways of looking at this problem. Yeah, so whether you define an imprecise model as a set of probabilities or a set of expectations, which is one way, or you define them as a lower expectation operator or an upper expectation operator, doesn't really matter. It's more to one. Okay. Right, so we have this little exercise. How much time do I have left?
34 minutes. 24.
Yeah, okay. Let's take about, let's say, it's a very easy question. Looking at a two-dimensional model. So heads and tails only, flipping a coin. You can prove in general that any lower expectation for these two outcomes, heads and tails, is of this form. So you have a precise probability, a precise mass function P on the one hand, so P is a mass function, probability of heads, probability of tails, so P is a mass function. This P is a mass function, so the sum of P of heads and P of tails is 1. So what I have here is the expectation of the gamble G under this probability model. So what is here between the square brackets is the expected value or the expectation of the gamble G with respect to this mass function. I multiply this by 1 minus epsilon, where epsilon is a number between 0 and 1. And I add epsilon times the minimum of G. So I have a convex combination of two models, a precise one, and this is the vacuous model. This is a model that gives me the minimum of the values of two. And you can prove, and this is for your homework, that any lower expectation on a two-dimensional space has this form. So it's always a convex combination of a precise model and what we call a completely vacuous model. That's homework. That's not the question here. I'm going to assume now that we have no reason to prefer heads over tails. So I'm going to use a symmetrical model where the lower expectation is equal to the lower expectation of heads, or the lower probability of heads, is equal to the lower probability of tails. So how the symmetry between heads and tails, there's symmetry, so the lower expectation for heads, the lower probability of heads, and the lower expectation for tails should be the same. And I ask you which lower provisions correspond to this symmetry requirements. So what can you derive from this symmetry requirement? And then quickly draw the coherent set of desirable gambles and the mass functions. Or the sets of mass functions. So the first step is impose the symmetry requirement to reduce the p's and the epsilons, to impose conditions on the p's and the epsilons, because those are the things that are still free. Then once that is done, look at the equivalent models, find the equivalent set of desirable gambles and mass functions. So let me the lower expectation of the indicator of heads. I use the formula and plug the indicator of heads, replace the G by the indicator of heads. I find this is equal to 1 minus epsilon times the probability of heads, because the minimum is equal to 0, right? The indicator assumes the value of 0s and 1s, so the minimum is equal to 0, and the lower expectation of the indicator of tails is 1 minus epsilon times the probability of tails. They must be equal. So there's two possibilities. If epsilon is equal to 1, then there's not much I can say. That's actually, but if epsilon is smaller than 1, then it follows that the probability of heads should be equal to the probability of tails, and therefore should be equal to 1/2. And therefore, I always find that the lower expectation operator for any G is in this case equal to, what is it? 1 minus epsilon times 1/2 the value of heads plus the value of tails plus epsilon times the minimum of the value of heads times the value of tails. So this is all of it. So the symmetry requirements reduces to forcing this precise probability in here to become air. There's still the precision, there's still this epsilon. This also works, of course, if epsilon is equal to 1, because then this drops out. This is the solution. Then, yeah.
I have to ask about a different case.
Okay. And then, how can we draw it? In this two-dimensional case, I have a set of desirable gambles. And what you see is that this expectation is completely symmetrical if I change heads and tails. Yeah, so this means that if I draw a set of desirable gambles, the part that is here must be, there must be this symmetry here between exchanging heads and tails. So my set of desirable gambles must look something like must be symmetrical with respect to this line, so it will look something like this. So it could be this if epsilon is equal to 1, we get this. We get this semi-plane if epsilon is equal to 0, this is epsilon equal to 1. And we get a model that goes like this if epsilon changes. Corresponding set of precise probabilities. Let me concentrate on the probability of heads. The probability of heads is this guy. Yeah. This is the lower probability. The lower bound for the probability of heads is 1 minus epsilon times 1/2. So I find 1/2 times 1 minus epsilon, something here, and then the upper bound for tails is then symmetrically here. This is 1 minus. Yeah, this is also, this difference is also 1 minus epsilon. That's right. So if epsilon is equal to 0, this is epsilon equal to 0. In this case, I have a precise model equal to 1/2. If epsilon is equal to 1, I get the entire interval. And for epsilon in between, I get a symmetrical interval around 1/2. Given by this bound here. So this is 1 minus epsilon divided by 2. So this is also 1 minus epsilon divided by 2. Yeah.
What you present is a syntax issue.
Sorry?
What you draw here?
It's a syntax.
The syntax.
Okay. Yeah. So yeah, I'm drawing in there. Yeah. So concentrating on the probability of heads. I could do the probability of tails, and that would be all right. Okay.
Instead of using the formula, if you on the symmetry, the angles equal.
That's what must be equal.
For the angles.
Yeah, indeed. So you don't have to go through the, the desirability here will already tell you that your set of desirable gambles must be symmetrical around this. Yeah. So it's an indirection, indeed. Okay, so let me go on. We have about 10 more minutes. Let me finish this. So quickly to the conditional versions. Yeah. I'm getting really hot and tired. Forgive me if I pay less attention to details at this point. All right. So I'm starting from a set of desirable gambles, and I want to define a conditional lower expectation and a conditional upper expectation. What will I do? I will go through the conditional sets of desirable gambles. So the idea is, I have a set of desirable gambles D. I will condition it on A using the formula that we had before. Sets of desirable gambles. And so, in essence, essentially, what I'm going to say that the conditional expectation for G given A is the supreme buying price, not for D, but for the conditional version of D. So I'm going to condition my set of desirable gambles on A and use that conditional set of desirable gambles to define a price. That is the idea. So I have this updated set of desirable, or this conditional set of desirable gambles, and I'm using that to define a lower expectation. So I replace my D in the expression for a lower expectation by D given A. That's it. And also, for the upper expectation, I replace the D in my formula for the supreme, sorry, this must be infimum. That's a mistake here. So this must be infimum selling price based on this one. Now, because of this, essentially what we have up to something that is not really important is that this gamble is in D if and only if its lower expectation is strictly greater than 0. So here, this is almost equivalent to the conditional gamble being in D, apart from some positivity that I can get rid of. Is assumed or subsumed. And so this becomes equivalent to this. So G minus alpha is in the conditional one if and only if the called-off gamble is in D. And in this way, once I have a D using this formula with the called-off gamble, I get to the conditional lower expectation and the conditional upper expectation. So there's no problem with sets of probability 0 here in this condition. As soon as I have a set of desirable gambles, I can define a lower expectation and an upper expectation, both conditional. This is where I start from a set of desirable gambles D. Suppose that I start from a lower expectation, then what I could do is I can look at the strictly desirable gambles here. So the strictly desirable gambles are the ones which have strictly positive expectations. So this strictly desirable here means that the expectation of this called-off gamble must be strictly positive. So if I have a lower expectation, I can define a conditional lower expectation in this way. No problem. Those are the formulas. There's not much to say or to see there. You can just use them to calculate conditional lower and upper expectations. Final exercise. And 5 more minutes. It's fairly easy. Start from an expectation. So the lower expectation and the upper expectation coincide. You know that. So you will use these formulas. You will use the conditional formulas, but instead of having a lower expectation, what you have here is an expectation. So the idea is the expectation should be positive, and the expectation of this called-off gamble should be positive. So you have a definition for the lower expectation and the upper expectation corresponding to this precise expectation. The lower conditional and upper conditional expectation. Let's assume that the probability of A, meaning the indicator of the, the expectation of the indicator that this is positive, and show that the expectation of a gamble conditional on A is given by this formula. It's the expectation of the fold of gamble divided by the probability of A, and it's precise. And if I replace this gamble by the indicator of an event B, then I find as a special case that the probability of B given A is the probability of the intersection given divided by the probability of our base rule as a special case of this set in the precise case. So it's simple. Look at these conditions, simplify them, make sure that you can take the supremum and the infimum, show that the infimum and the supremum are equal to this value, and then plug in the indicator of B in here, and you're done. Great. Sorry, the second one?
Last line, the third,
The third line?
the last line.
Last, this one?
Yeah.
So the idea here, oh, that should be a certain upper. Yeah, you're right. Yeah, sorry. Too much copy and paste. I think you've suffered enough. I think it's time for a coffee break. Isn't that? Yeah. And I'll give you the solution when we get back. It gives me time for a coffee as well.